So unusual.
Okay.
There were a lot of movies in Russian about this, and she also was a beloved of Sergei Yesenin, who is a well-known poet in Russia. Of again, it calls a silver century of Russian.
What is the name you said?
Whoever
I don't know how it's
No,
called.
not the name. Part name is someone's name.
Sergei Yesenin.
Oh, I heard the name.
So you have a special speaker, a special subject. The shortest of these remotes should be.
Doesn't work that well though.
It's slow.
You have to,
Oh, there it goes.
you have to point it at a particular place.
Here is a Yesenin. I don't know this guy.
Maybe it'll work.
I can find you a Sidora.
I see some translated Bengali, it's a work.
You're on the record.
Thank you guys for coming. Today is, well, this presentation was supposed to be purely like a journal club presentation. But then I realized I'm lacking in some mathematical expertise in stuff I was about to present on. So now I'm kind of mixing a little bit of preliminary results from my related research and kind of a piece of literature that helps describe what I'm kind of doing. So we're looking into twisted graphene. So graphene, right, monolayer graphene is just unwrapping a carbon nanotube, which has been my previous presentations, right? But now placing a second layer, so a bilayer of graphene, and twisting that top layer by some angle, okay? And it's been shown in experiment that twisting it in small angles, or any angle that's quote unquote a magic angle, has some sort of superconducting properties. Like higher temperature superconducting properties specifically, and it's not completely well understood.
And what is superconducting, if we have forgotten?
So, the property of superconducting materials is that electrons have no resistance to travel throughout the material.
So there is no emission of phonons.
Effectively, yeah. There's no coupling; they can just kind of travel freely with no resistance. I don't know if there's a better description, but
But again, it's two sheets of graphene
Yep, a
twisted
bilayer.
with respect to each other.
Yep.
Right?
Yep, exactly. So I found this really interesting paper that I want to present, and it's just kind of taking the system as a toy model. So in this bilayer, these twisted graphene bilayers, if you look at the dispersion, you get two interacting like conical shapes, right? And that's just a well-known property of these twisted bilayers.
So does this have to deal with the inherent nature of graphene because they're like Dirac points?
Yes,
Okay.
but there's special, the distance between these points is modified now by this bilayer and twisting. So then the properties of these conical shapes, like the width and the height or the depth and the interaction barrier is modified. That's what's interesting. So just have that picture in your mind here. But then if you look at panel A at the top, you can approximate this as just from introductory quantum mechanics, right? It's just a finite barrier with an electron kind of going towards it and trying to overcome this barrier. And so these people here came up with this sort of an effective Hamiltonian 2x2 that has kx and ky kind of in terms of two other variables that they declare. But it's really simple, right?
But why it is a matrix? What are the components?
Well, I don't really want to talk about that because
So you know the answer, but we are not worth to hear it.
yeah, it's not super important to what I'm about to
Okay.
discuss here.
But is it the spin component or something different?
No.
Okay, it's a good intrigue.
What sort of
Yeah.
is it? Hamilton effect.
So they go ahead and solve this, and they show the energy spectrum result in terms of kx and ky in reciprocal space, and then they compute transmission.
But this is pure computations, right? Or they have experimental data?
Or it is pure theory.
Pure theory.
I mean, for this paper which you presented, I understand, but
Oh.
in general, are there any evidence? Are there any evidences, experimental sides that you can really control and so on? Anything?
Yeah, I believe so. Yeah.
Believe is not a
Well-
very good word.
Well,
for
yeah, I
science.
have multiple papers that show that
Okay.
there's new like Van Hoff singularities that come from this twisted stuff, and it kind of couples with what they're talking about in this paper. But
So they can really realize the system in
Yeah.
real experiments.
yeah, more complicated than this model. But
Okay.
yeah.
Or maybe it's electron and hole, these two components. On the previous slide, the intriguing question that you decided not to answer, is it like for electron and hole?
They talk about it in terms of that. Yeah. And I'll actually say that on like the next slide or the slide after that. But this whole paper talks about this transmission coefficient, so like the probability of going through the barrier. So you can see here, they're making a plot of effectively the electron's velocity through this, or initial velocity through this barrier. And so they can compute the transition probability as a function of that initial velocity for three different heights of the barrier, respectively to the initial velocity of the Fermi velocity.
And where the barrier is coming from?
Between the Dirac points of dispersion relation.
Okay, what is x-axis on the A panel?
You're kind of traversing this.
Well, on the panel B, it looks like momentum, right?
Mm-hmm.
And on the panel A,
Well, they're making just a correlation between this in position space is commonly referred to, but then
so there is no rigorous definition of the x-axis in the A panel? It's just...
No.
Okay.
Yeah.
So it's very abstract.
Yes.
Okay.
So if you change the del U, how will you change the D? You don't affect the D too?
The del U affecting the D. Those are two independent parameters, right? The height and the width. I mean, that's specific to the system you're looking at, but in this model, they're two independent parameters.
No. So what would be position of your singularity, I mean this singular point in the momentum space if you change the U?
Say that again?
I mean these two, what's it called? These, I don't know the name.
Well, okay, so think about this very abstractly in like reciprocal space. That would just modify this distance. Type
Oh, okay.
of a thing. I think that's what they're getting at here.
Oh.
A toy model from introductory quantum mechanics in
So
position
if
space.
you increase the distance, U will be higher, U should increase too. Is it like something like that or?
I think D just says how far away are the 2 points,
Mm-hmm.
and delta U says how big is the barrier.
Yep, so I'm just trying to think if I change the distance, should it increase the barrier too?
Well, they're probably coupled in real life,
Coupled,
but
yeah.
in this model, it doesn't matter.
And actually, you probably told this. They changing the twisting angle or they don't? Or they fix it?
For this model, they're just kind of not discussing that too much. They're just talking about kind of bilayer
But in
intersections.
their case, it's semi-metal, right? It's not opening the gap, it's not becoming semiconductor.
That I will also kind of talk about on like the next slide.
But they change it due to these parameters, D and delta U, right?
Mhm,
And they show that you can go.
mhm.
But these parameters, what I don't understand, because my understanding, I can, like, looking on your figure with these surfaces, right? So you can imagine that if you change the angle between
Mhm.
two lattice, two surfaces, right? So this kind of change in the attachment points, and you might really kind of go when one will be on this A vector, another and the other, and this is actually opening the gap, right?
So
but I don't understand how this parameter is connected to the
it's not.
D and delta U.
It's not here.
Okay.
That's not taken into account. Yeah, so in real plots like this for twisted, these don't look this nice, right? So this could come up and have more interesting shape, as well as being twisted in the KX, KY plane.
Mm-hmm.
Yeah. So they're not taking that
into
account here. They're just making it very simple for like a first approximation to this.
And again, what is the goal then for this model?
To
show what?
Well, to show the transmission. So you're able to tune the transition based on this this idea of these conical intersections and the weld parameters. So if you
So we know particle in the box or whatever going through this step barrier or whatever, of course changing the size and height is tuning of the actual energies and penetration and your wave function tunneling kind of properties. So it cannot be a new idea from that point of view. So I mean, clearly it will, but I thought that they should connect it to some realistic structures, right? And then maybe connect how these parameters connect into real, not just model parameters, but to real systems. Do they?
Not really. This is the only figure that they show that connects to real systems. They sort of solved their model system for a little bit more complicated case that they didn't really talk about, but it was more so a real system. So this left two panels, A and C, are supposedly for a twisted graphene structure. And so they're showing this transmission coefficient as a function of sort of the incident angle that the electron is traveling toward the barrier itself. But that's the only correlation they make to real systems. And then the right columns is their purely model system at the same time. But really, this paper is not too in-depth for real stuff.
So this can be the task for your quantum mechanics course. See how the wave packet is moving through this barrier and kind of connected to the
We solved that equation right.
So yeah, so then
someone needs to volunteer to do this task. So the first one needs to make a very strong motivation talk.
Here is a volunteer.
I think there's a voluntold.
Okay, sorry to interrupt you.
Good idea.
So as a logical extension to this plot, so they're plotting transmission probability as a function of the incident electron's energy. Now they're flipping it and plotting it as a function of the barrier height at different values of incident energy.
No, it's mine.
That was my key.
And so you can see for this very small incident energy, you can see that there's no point here for barrier height. There is zero transmission, and they don't talk too much about why there is at larger incident energies. But you can see that there's a.
So can you explain what does it mean? No transmission. Transmission.
Yeah. So there's no probability that the electron will go from one conical surface to the other.
And physically, what does it mean?
The electron's movement is inhibited.
But so your electrons will be just localized in some specific, because you're doing it in a K space, right? They solve it.
Yeah, they're localized.
But you can always go to the XYZ coordinates, right? And then it means that you will have really electron being trapped, right? Somewhere on that side, around some atoms or around that atoms, right? Or not? If it cannot go from one well to another, it means what?
It's localized in K space, so it's more or less not as much localized in position space, right? Because if it can't move out of this well, right, in K space, if you transfer that to position space, it should be the opposite. But only for those momenta that are allowed in that well. That's my interpretation of the results here. Because if it's localized in that well, you know that its momenta is restricted to this maybe circular space in K space. So for some values of Kx, Ky that it is sitting in, you can just flip out and only the electron will have those in position space. So it'll be restricted in momenta, but it shouldn't be restricted in space per se.
So, right, Heisenberg uncertainty.
Effectively.
No momentum.
Yeah.
We don't know as much
That's
the
my
position.
argument.
Yeah. That's all.
Okay.
Okay, but what I don't really understand, and pretty much this is the only sentence that they say about this, is, so you can see on the top panel in black for low initial energy of the electron, there's no point in this range of barrier height that the transmission probability is 0, but there's increasing oscillations with the fact that the barrier height is increasing. But then for larger values of the initial momenta, or initial energy, you can see around 0 barrier height with respect to the energy, there's complete reflection. And they don't talk too much about this, and I don't really understand why, but they say for the middle and bottom panels, we see that there was no reflection due to the system's inability to produce an electron hole pair. But it doesn't make sense to me because the energy is greater in those two than in the first one for the electron. So I would expect it to transmit or have a better chance of producing this effect. But then they correlate it to the conical intersections here in a nice graph. So the black curve is more so aligned and touching, and the red and gold or whatever that is further and further out.
What's E divided by EV?
It's just a normalized energy with respect to the Fermi velocity energy.
Oh, okay.
And they just say that in these two panels, it's less than the gap for that dispersion intersection, that conical intersection. But maybe I'm just lacking in the theory here, but it seems backwards in my mind. So then here, they kind of explored the oscillations themselves and talk about that in terms of the barrier height as well for different widths of barrier in terms of nanometers and 100 nanometers. So here they say it couples to the barrier width in an inverse relation that you can see here, the periodicity, I mean. So they show that nice relation.
So do they do this in a single barrier or in two wells? Because looking at panel A in your figure, it looks like they have the electron, a hole, a barrier, and then nothing. So do they do it periodic like Dimitri's code? Or do they actually have like two wells that do not allow it to go, if it hits the barrier and it comes back and then it loops around?
If that's the infinity, but in this case it's not
Well,
infinity.
You can think of there being an infinite on either side. Because in here, it just goes up to infinity.
I understand in B, but I'm asking about their model system. Because
Just think of an infinite potential right here. So it's confined.
okay,
I mean, it wouldn't be vertical, it would be
so
harmonic.
they don't allow it to go through the backwards path.
I mean, they don't care. That's the reflection. They don't talk anything about the reflection.
Okay,
So it doesn't matter. Does that make sense?
somewhat.
Because of course, if there is reflection, it'll come back, hit the other side, and then it'll try again, right?
But then how do you determine which is transmitted and which is reflected?
Well, the initial impact, there's a transmission and reflection, so it probably doesn't consider the okay, I see, that may be what you're asking.
Yeah.
I got it. But they don't talk about that at all, that's a pure assumption. Yeah, and so here's the the last figure they show, this is the only comparison to real systems. The left panel here is their computed results for twisted graphene bilayers dispersion relations, and their model system on the right column. Okay. And they show that the right column is perfectly symmetric about the incident angle. So I modified their figure there and put in the theta and a red arrow, kind of hint at the angle that they're referring to my best understanding. And so in the real system, they show from that dispersion relation that the conical intersections aren't symmetric necessarily, and so the incident angle here doesn't necessarily have to be symmetric about 0 either. And they claim that is a nice result. So in reality, that's a big issue to worry about. But as I said, in twisted graphene, the conical shapes aren't necessarily perfectly nice looking either.
Is it the first time you are speaking about twisted graphene?
First time first time in this talk?
In this talk.
Yep.
No. Oh, he was talking about twisted surfaces.
Well, most of their talk.
Here, twisted means what? Defects?
Buckled? Or
Just
twisted?
rotation.
So it is not one graphene sheet.
True, bilayer.
Bilayer.
Maybe was that not clear? Sorry.
It's still
No.
the same system from the very beginning up to this
Yep.
point.
Yep.
So everything you are speaking about is about bilayer.
Yep.
And this figure on the left is the only one where you have angle offset between the layers.
Yes.
Before, you didn't care about it.
In their model system, they don't care about it because they're doing a very rough estimate. Because in non-twisting, it looks nice. The conical the dispersion relations look smooth and very symmetric about themselves radially for each intersection. But then when you twist it, it doesn't necessarily have to be like that. So I believe they took data from twisted and applied their model to maybe that dispersion relation, and then computed these results from that.
So the main message is that twisted graphene is superconducting.
It's more tunable. This transmission is more tunable. That is their result.
Would it be correct to tell that only bilayer is superconducting while monolayer is not?
They do not say anything about that.
But what is your impression? Can single layer without second be superconducting?
Well, in theory, it can, right?
But in what you're discussing, it is always bilayer.
In everything they discuss, it's always bilayer. Yep.
So there is an expectation that bilayer is
It's better. It's higher temperature. Yeah, is the idea. Yep. Okay. So this is the last figure that they have. So some conclusions from this paper are that the twist angle of the bilayer will drastically affect all properties of the dispersion relations, including all the parameters they include in their model system. Then the traveling electron or quasi-particle can be treated in this model Hamiltonian that depicts that transmission through that finite barrier that they approximate as a rectangular barrier. And one of the approximations that went into that Hamiltonian is that the twist angle is small, and the electrons are low energy in general, with respect to the Fermi energy that was listed earlier. So there's better understanding of how the twist angle shapes these conical dispersions, as shown in the angle dependence, which allows for another parameter to be understood here. When you twist them, those conical intersections in the dispersion relation don't have to be nice looking per se. Okay. So that's the whole idea that I'm trying to understand here about these twisted graphene bilayers. So now we can go to my preliminary results. Very preliminary, as you can see. So what I'm doing is I'm currently just testing geometry right now to find what I want to do in general. So I've just so far tested the PBE and the PBE with a D3 dispersion correction, which I'm 100% positive is needed before I even started, but I was testing anyway. So I'm testing 3 different systems right now. So I'm doing, of course, just a bilayer that has no twist angle for reference. I'm doing a twist angle of 6.01 and 21.8, which are two reported magic angles for the superconductance. But unfortunately, superconductivity is shown to be better for small twist angles. So there's one that's 1.02 and 1.16 or something twist angles. But the superlattice that results from these twist angles is of course very large for small twist angles, and smaller as you increase the twist.
Can you derive an equation for number of atoms in superlattice as function of twisting angle?
Yes, people have done it. It's in one of the multiple papers that I'm looking at.
But can you just verbalize it roughly? Is it like
Well, it puts in terms of
maybe 1 over angle?
It's-
So what angle goes to 0, the number of atoms goes to infinity, or it's
well, it depends on the lattice sectors, N and M, for the superlattice on the graphene sheet. I don't remember exactly how it looks, but it goes like that's the sign of theta, one of them.
so angle smaller than 6 degrees is not tractable.
Yeah, I'll show you in the next slide, I believe. Yes. So I created a supercell of 1.05 degree twist, which is also one of the reported magic angles. And from point to point in the superlattice, it's 6 nanometers about. So
this black square or gray square is not just gray. There are many carbon atoms and bonds between them.
hundreds and hundreds, yes. And then multiply it by 2 because it's got depth of 2 bilayers.
So along this 20 nanometers, how many carbons?
Well, this is thousands.
No, not total.
Oh.
If you line them along this arrow, along 20 nanometers, just to see the scale, because maybe from last row or maybe on recordings, it will look like continuous gray area.
Well, you just define
How many carbons per nanometer? What's the distance carbon?
carbon bond 1.5.
So like six carbons
Yeah.
per nanometers.
Yeah.
So like 120 along this line.
Something like this,
Okay.
yeah. Okay, so obviously this one is untractable because the supercell would be, even just in this red hexagon, the supercell would be hundreds and hundreds and hundreds of atoms. So now, if we increase the angle a little bit to 6.01, now it's only 3.6 nanometers from 1.2 another. So that's much more tractable, and you can see the the nice overlapping atoms periodically. It produces a kind of a hexagonally packed structure. So now if we zoom in, we can call this a unit cell. So you have 4 overlapping carbon atoms here and 1 in the middle. And here is your smallest simulation box that you could choose. So this one has something like 700 some atoms in it, so it's still quite large even for 6 degrees. And you can increase it again to another magic angle of 21.8, and it gets even smaller. So here it's only 6.49 angstroms between overlapping atoms in the cell, so the unit cell can be much smaller, about the size of all the red dots I'm showing. Okay,
So I have a question before you go on.
yes.
Are the planes are they like coplanar,
Yeah.
or is there deviation, or is it just like our eyes seeing them when they line up exactly, which makes it kind of wavy? Like for the really big one, like this, it almost appears that like it goes in and out of the board.
Yeah.
So it's just our eyes
It's just
seeing.
It's
Okay.
just the overlapping, the change in overlap as you go out from these.
So it starts planar and you let it do whatever as it optimizes.
It's always planar.
Always.
This can be periodic. I'm just showing sheets right now, but in the cell it's periodic, and they're always planar. And this is just a visual effect that you see. Okay, so the very preliminary results I have are now being shown. half now being shown. So the 0 degree twist angle, so just a regular bilayer optimized with high precision at PVE and PVE with D3 dispersion correction, show these density of states, and for the 21.8 degree shift, it shows those density of states for PVE and PVE plus D3 as well, which they look okay because for bilayer graphene, there is a band gap, especially for the twisted ones, and so this isn't too surprising, but I don't have too much to compare to necessarily. And I can also show the 6.01 result, which I find a little troubling because the band gap is very small, and I don't know why that one would be different. So I have yet to look into that.
And you do everything at gamma point?
I do everything at the gamma point, so that's something I can look into as well.
And how happy you are about using gamma point, and what do you see positive and negative about it?
What do I see positive and negative about it? Well, I'll need to do multiple K points first, and then I can respond to that question.
But is there any value in results without gamma points?
Possibly not, because of the conical intersections aren't at the gamma point,
Okay.
like we discussed. So possibly this is low coverage so far, because it could just be picking out a point on the intersect or the conical shape. That's not the minimum, but got to start somewhere.
And the number of atoms in each of these simulations is different. You are not increasing the small cell,
No.
replicating it to have the same number of atoms.
No, I'm not. So 96, 728, and 112. So there's many published results, but this is one that I find particularly helpful for the interlayer distance, which is what I'm starting to try to compare to with the literature. So they report these values for AB stacked, which is just 0 degree shifting, just a regular monolayer that's shifted due to the overlapping hexagonal rings. And then you have the twisted bilayer on the bottom plot. So, and here's my results for just the interlayer distance. And so you can see here that my red corresponds with their red and my green corresponds with their green here. But I'm not too far off, I guess, but then again, I'm not sure how far off is too far. So I need to figure that out as well. Hopefully including multiple K points will give me more reliable data, at least, and give me some sort of reference to compare to for these results. And just to compare, I just did a single graphene monolayer and expected a 0 homolumo gap, but I didn't get that. So including multiple K points like we just discussed, hopefully will get me to 0 at a different value. Okay, so future work obviously is a big part of this presentation. So I want to explore these dispersion relations, so including multiple K points and trying to recreate these conical intersections. And so some people are discussing whether DFT is good enough in the literature. So obviously I'm also concerned about this. So if it's not good enough for monolayer graphene, is it good enough for twisted bilayer graphene? Possibly because the twisted bilayer graphene is known to have a little bit more open of a band gap than any of the other ones. And in addition, what prompted me to think about this third big bullet point is a talk in the physics department last week. I think it was last week or maybe it was the week before, about Dr. Yongki Choi in the physics department. One of his students is doing graphene. He's attempting to look at the conductivity relations of graphene and bilayer, no twisting, just bilayer graphene, with the addition of potassium and lithium ions onto the surface in varying concentrations. And so it seemed like they didn't know really what was happening. They were just able to just measure basic conductance for their systems at not near 0 Kelvin, but somewhere in the tens to to room temperature.
How do they control the twisting and non-twisting experimentally?
They have to put substrates around, and they kind of sandwich them together.
So is there like a ideal, if you take two graphene sheets and throw them together, do they have like a specific
As a function of
orientation
the angle,
that they
where's
like?
the minimum?
Yeah.
Yeah, I don't know. I guess I haven't read anything about that. Obviously, there is one.
And then you think that that would depend on the, like, where the edges are cut? Or if they're so big
Well, in experiment, they're so big.
that the edge effects don't matter?
Yeah, of course. And in our systems, of course, periodically, hopefully that shouldn't matter either. So one could potentially do sample the angle. So maybe that'll be fun to do just for interest. But
It's a continuation of you guys' question. How does exfoliation energy depends on twisting?
What was the question?
Is there exfoliation, like binding of two sheets to each other? Is there preferred?
so here they report some values for the exfoliation energy for
Oh.
just bilayers with no twist, and then one single twist angle of twisted bilayer graphene.
So when you twist, it is less favorable.
That seems to be the results from just one twist angle, so I'm not sure how general that can be, but yeah, but one
But isn't virtually all of these are around KT?
Mhm.
So then there might be a local minimum.
Half KT or third KT.
Mhm.
What? I thought KT was 25. Oh yeah, half of it, yeah.
Yeah.
Okay. So they, experimentally, they might not actually have one that will always occur, since if these values are correct, they can
Well,
kind of.
they fix it though. Remember, it's just on a substrate, so it's they claim that it's fixed to that substrate, and so they just sandwich them together, and then I think they can do neutron scattering and stuff to make
But
sure.
if you just throw two together and let them be without fixing it.
Yeah, I don't know the answer to that. Okay, so I'm thinking to do, I was hoping to include it, but the preliminary runs for this isn't done yet, but I'm thinking to do potassium and lithium, focusing on potassium because I see more of that, in different concentrations to give some novel effects for this twisted bilayer stuff. So I haven't seen this cation addition in twisted bilayer papers that I've read. So I'm wondering if there's a reason, because nobody's ever talked about this, doping those, but
How do you deal with charge? Because if you have one potassium, it's gonna be infinite charge as you go to the periodic cell. So do you know if they have counter ions? So they put something other than potassium, but it doesn't affect anything.
in experiment, I don't fully understand how they do it exactly, but they ionize this potassium and then somehow sticks in some concentration that they know how to do. But that's a little bit beyond what knowledge I have right now. But in calculations, yeah, you have to think about that. And I haven't thought about it too hard yet, but this is the direction I want to go.
I think I was talking to John, and in VASP, you can do something to minimize that effect. But I don't remember what he was saying. Dimitri, do you know anything about the growth of charged species in unit cells in VASP?
Taken care of.
Oh, it is?
Yes.
Okay. Good.
Okay, so, and then also in these works, they talk a lot about clustering of these cations into lattice structures. If they're at, like, due to thermal energy, they can hop between rings, right? And if they encounter another one, sometimes they stick. And if multiple of them stick, they form these little small clusters. And nobody really knows how that affects things, and they don't really know if it's actually occurring. But there's been some reports of this hopping rate between ring to ring. So possibly I can get an estimation for that to see how fast one can hop to the other, and also get a good idea as if the concentration is large, how likely they are to form these small clusters. So just some thoughts about what to do next. And that should be it.
So, do we want to entertain Braden with any questions? How layers help each other to conduct electricity?
How layers help each other.
Earlier you've told that it's somehow more efficient to be superconducting with two layers rather than one layer, so they kind of help each other.
Yes.
So what's the mechanism?
And also at the beginning of this talk I said that this was supposed to be more of a literature review rather than what my preliminary results are. And then I said that the math behind a lot of this stuff is a little bit beyond me, so I didn't want to present on it today. But your answer is enveloped in that math somewhere. But I see a lot of papers about electron hopping between them as well.
Between them?
Between the layers. So, but that, again, that math is both.
So while practicing conductivity, an electron goes part of the way on one surface, then jumps on another one.
Yeah, it exists maybe between them, and so.
And then jumps back. Okay.
So it's not a lateral electron flow, it's through the cross-section of electron flow.
Well, I mean, the idea is that it laterally moves, right? That's what you would want it to do, but possibly there's an attraction to both surfaces, and that aids in the movement between, so it kind of pulls it maybe away from the ions. It's just a complete guess. I'm not 100% sure yet, but it might pull it away from the ion, allowing it to move more freely between the layers. And how adding potassium and lithium to that system, with that argument, how that helps, I'm not sure. But that's also something I'm going to look into.
I think Fatima had a question.
Okay, so your potential barrier is between these two layers of graphene?
You're referring to the model system at the
I'm
beginning?
talking about the model, yeah.
Okay.
The first question.
In general, no. It's just the model system was in K-space, kind of. So it was a restriction on momenta, not position potential barrier, kind of. Maybe I didn't convey that super well. But in momentum space, there was a barrier in the dispersion relation. And so they were just comparing that to the finite barrier in position space that everybody knows from introductory quantum mechanics.
Okay, and electron transmit through the barrier.
Through the?
Barrier, the potential barrier?
Yes, yep.
So how? Do you know the, like, is it quantum tunneling? Or?
Yep, tunneling, yep, exactly, yep.
So you do have literature review on assessing through some models the conductivity or transmission, but if you would do the whole procedure with your models, what would be your observable? How would you compute the transmission or conductivity at ab initio level? What is your plan?
Have no plan currently. I'm just trying to find a good model to start out in, that I reproduce these geometric and ground state effects that I'm looking into.
But if you need to do the same as music jazz players do, improvisation. So if you want to do improvisation on your plan, suppose that you already have model that satisfies all criterion, and you still are posed in front of problem to find conductivity and show that it is equal zero. How will you compute it? Just share your vision or ideas.
Well, One needs to compute the phonon modes and see how the electron structure couples with that, right? Because that's how conductivity can be thought of, right? How these electrons can couple to the modes, and if there's not a lot of coupling, it can be free to move.
So you want to consider the process of electric current as scattering from ions and dissipating of electronic energy into nuclear degrees of freedom.
Which you hope is minimal, yes.
And if it is minimal, so it's very similar to adiabatic dynamics with
Kind of.
cooling of carriers.
Kind of, yeah. That's my interpretation of this, but I'm not.
Interesting, interesting. And what is the current operator, and how does it relate to your problematics? No, just improvisation. What is electric current?
Electric current is the movement of electrons throughout space.
So movement means what about their velocity or momentum?
It's non-zero.
Okay. So how does current operator relates to momentum operator?
How does it relate?
Uh-huh. Nicely.
Yeah, okay.
Indirectly.
Because I remember learning of probability current and stuff like this. I assume it's related and looks like that, but
So how would you find matrix element of momentum or current operator or momentum operator?
how would I find?
Yes, if you have atomistic model, set of quantum orbitals.
The answer to this question is really easy, but it's eluding me.
Okay. What is the relation between momentum operator and transition dipole operator?
Momentum operator and transition time.
Like matrix element of transition dipole and matrix element of momentum and matrix element of current operator.
Well, there's a DDX instead of an R, or not an R, but there's a DDX.
But if you select pair of initial and final states, compute all these operators, would they correlate between each other? Maybe. You don't exclude such an opportunity. Okay, interesting. More questions? So, by some reason you prefer planar geometry.
Yes.
Suppose that you start to roll, not you start to roll, but you do roll the graphene into carbon nanotubes
I've looked at that already.
at larger.
It's impossible to choose one that is computationally feasible and that the lengths match up with the units.
So can you explain on this like analogy between bilayer of graphene and coaxial carbon nanotubes of different chirality?
What do you mean?
Coaxial, like one
I know.
one nanotube inside of another one.
What about the relation? That it's impossible to find a carbon nanotube that's computationally feasible, or what?
No. Is it possible to get superconductivity in the set of
Well, that was
coaxial nanotubes instead of bilayer of graphene?
that was the idea, and I'm not sure how they would relate to each other. I'm not sure if one would be better than the other for any particular reason. I don't know the answer to this.
But like, what are pros and cons for this idea?
Physically or computationally?
Both.
Well, computationally, I did a search of parameter space for carbon nanotubes, and you need tens of thousands of atoms to find the right unit cell length to do this. And so it needs to be like 30 carbon nanotubes, or N30 equal M30 carbon nanotubes. So they're just absolutely huge and experimentally unfeasible, because the larger you get, the harder it is to make them, I guess, reliably. Physically, I don't know about the conductance between the two and how that would affect bilayer stuff.
So in order to get the preferable twist angle one would need really large diameter nanotubes. If you do like 6.5 and 7.6, the angle will be not preferred if you like put one in.
Well, I made a script that for fixed angle it computed all possible combinations of N and M for carbon nanotubes, and I ran this for multiple different angles, and for no angle of twist was there 2 carbon nanotubes less than N equals 20 and M equals 20, such that the unit cell length was reliable. And in addition to that, there's another restriction that the diameters are the same as, or about the same as the bilayer and graphene distance apart. So there's way too many things, and then to do that you need to go up to, I tested for N to equal 100, M to equal 100, and I tested all those combinations, and there was nothing nothing within what is reasonable to do. Even in real life, there's no combination of them that is good.
Okay, more questions to Braden? More questions 1, more questions 2, more questions 3. Let's thank you once again. Anyone has objections against declaring wish of a nice weekend?
No.
Okay, have a nice long Memorial weekend. See you next week. And there is a volunteer for next Friday.
Who?
Or there is a person who...
Oh, is there a volunteer?
There is a volunteer. There is one volunteer, but if there are more, just sign up.
Who's the volunteer?
He knows.
That's me, I guess.
Okay. Let's depart in peace.
In peace.